ME204, Particle Kinetics using Angular Impulse, Angular Momentum, and Conservation of Angular Momentum. Let's do a little bit of review of statics. If you had to describe a moment of force in plain English, how would you describe it? Perhaps you would say that it's a torque or leverage caused by a force acting at a certain distance from a pivot point. In equation form, a moment is equal to a force times a distance. However, the force and the distance must be 90 degrees to one another, or perpendicular to each other. We've talked about linear impulse and momentum and defined that equation. What if we went through these equations and multiplied both sides of the equation by a perpendicular distance, d? We would get something that looks like this. Well, we know that a force times a perpendicular distance is a moment. So let's go ahead and replace all those forces times distances with moments. Now you can see at the bottom of the page that we have mass times a velocity, which is our initial momentum, times a perpendicular distance, plus a moment times a change in time is equal to our final momentum times a perpendicular distance. This is angular momentum. Let's look at linear momentum versus angular momentum. Linear momentum is simply our mass times our velocity. Our angular momentum is the mass times the velocity times a perpendicular distance to a pivot point. You can think of this as a moment of the momentum. Here's our momentum, and this would be our perpendicular distance to the pivot point. Remember that a moment of force is the cross product of the force and the perpendicular distance to the pivot point. The same can be said of our moment of momentum. It's the cross product of the momentum and the perpendicular distance to the pivot point. Remember that in energy, we weren't as concerned about the direction of our kinetic energy. However, for linear momentum, we were dealing with vectors, and so direction was important. Angular momentum also has a direction, and it's important as well. We determine that direction by using the right-hand rule. Counterclockwise around an axis would give us a positive direction, and clockwise around an axis would give us a negative direction. If we look at the z-axis in this little figure in the bottom left-hand corner and rotate counterclockwise around that axis, that would give us a positive angular momentum in the z direction. However, if we rotated around that axis clockwise, it would give us a negative angular momentum in the z direction. What if we had a rotation around the y-axis in this direction? Using the right-hand rule, this would give us a positive angular momentum in the y direction. If that rotation were in the opposite direction, that would give us a negative angular momentum in the y direction. Now let's take a look at an example and find the angular momentum. Here we have a simple mass of 5 kilograms that's traveling at 8 meters per second, and it's 2 meters from the pivot point and is attached to that pivot point, so it's rotating around that point. Well, our angular momentum is our mass times the velocity times the perpendicular distance to the pivot point. In this case, our mass is 5 kilograms, our velocity is 8 meters per second, and the perpendicular distance is 2 meters. So we would have an angular momentum of 80 kilograms meters squared per second. Now let's look at linear impulse versus angular impulse. We defined a linear impulse as the integral of the force with respect to time, or if we have a constant force, it's a force times a change in time. For an angular impulse, we have an integral of the moment with respect to time. Or if we have a constant moment, then it's a moment times the change in time. We also know that a moment is a force times a perpendicular distance, so we can write this as a force times the distance times the change in time. This works when we have a constant moment or force. If our moment or our force is not constant, for example, it's a function of time, then we would have to integrate with respect to time to calculate the angular impulse. Let's find the angular impulse if we have a 50 Newton force acting at 60 degrees on our 5 kilogram block for 3 seconds. Again, that block is 2 meters from the pivot point. In this case, we need a force that's perpendicular to our radius arm of 2 meters. In order to get the perpendicular force, we'll take our 50 Newton force and multiply it by the sine of 60 degrees. Our angular impulse is a moment times a change in time. Our moment is 50 times the sine of 60 times the moment arm of 2 meters times 3 seconds. That gives us 260 Newton meters seconds. Now let's put everything together. For linear impulse and momentum, we have a mass times a velocity plus a force times a change in time is equal to our final mass times velocity. Or if we don't have a constant force, we have our initial momentum plus the integral of the force with respect to time is equal to our final momentum. For angular impulse and momentum, we have a mass times a velocity, our momentum, times a moment arm, plus a moment times a change in time is equal to our final momentum times a moment arm. Or if our moment is not constant, then it's our initial momentum times the moment arm plus the integral of the moment with respect to time is equal to our final momentum times the moment arm. Now let's put this all together in one problem. How fast will the block be going after 3 seconds starting from rest? Well, let's use our angular momentum equation. We have our initial momentum times the perpendicular distance plus a moment times the change in time equals the final momentum times the perpendicular distance. Our initial momentum is 0 since we start from rest. Filling in the rest of the equation, our moment, 50 sine of 60 times the moment arm of 2 meters times the time of 3 seconds is equal to our mass of 5 kilograms times our final velocity times its moment arm of 2 meters. Solving for the velocity, we get that our final velocity is 26 meters per second. What if we applied a torque or a moment at the center of rotation rather than applying a force at the block? Now we have a torque or couple moment of 70 Newton meters acting for 3 seconds. Again, our equation is the same. We start from rest, so the first part of the equation is 0. Our moment is 70 Newton meters, and it's applied for 3 seconds. So filling in the rest of the equation, 70 times 3 is equal to 5 times our final velocity times a moment arm of 2 meters. Solving for our final velocity, we get a final velocity of 21 meters per second. How fast is the mass moving when the length of the string is cut in half? Now we don't have any external moments, we just reduce the length of the string by 1 meter. Well, here's our angular momentum equation. There's no external moments or forces, so the impulse goes to 0. We're left with the mass times the initial velocity times the initial distance is equal to the mass times the final velocity times the final distance. Filling in what we know, a mass of 5 kilograms, an initial velocity of 8 meters per second, and a moment arm of 2 meters is equal to 5 kilograms, our mass, times our final velocity, times a new moment arm of 1 meter. Solving for our velocity, we get our final velocity of 16 meters per second. By pulling in half of our string, we doubled our speed. So we have our equations for linear momentum and linear impulse. Now let's add to that our angular or rotational momentum, which we can also think of as a moment of momentum. This is a mass times a velocity vector crossed with a radius arm to the pivot point. If I have a mass of 1 kilograms going 2 meters per second, that's 2 meters from our pivot point, then I can take the cross product of 1 kilogram times 2 meters per second for my momentum in the j direction, crossed with a negative 2 meters for my radius arm to the pivot point in the I direction, and that will give me a positive 4 kilograms meters squared per second in the k direction. For an angular impulse, we have a force vector crossed with a moment arm times a change in time. If we apply 2 newtons for 5 seconds to our mass, that's 2 meters from the pivot point, then our equation becomes 2 newtons in the j direction crossed with negative 2 meters in the I direction times a scalar of 5 seconds. That gives us a positive 20 newton meter seconds in the k direction, which is equal to 20 kilograms meter squared per second in the k direction. Our next topic is impulse and momentum, rigid body kinetics.